So the folks at Q-Chem had asked me to have a discussion about the solvation models that are available in Q-Chem, because my group has been responsible for implementing some of that technology. This is sort of intimidating because continuum solvation theory is a vast area of quantum chemistry that goes back a lot of decades. And we've only been involved with this for a few years, but so I thought that I would take the strategy of simply trying to explain to you some of the theoretical background and some of the nomenclature, and then run through some examples that are largely intended simply to show you how to set up continuum solvation jobs in Q-Chem, rather than trying to really get at any of the chemistry or physics of solvation, because I don't see how I can do that in 45 minutes to an hour's worth of time. But maybe I can give you some insights into the theory, some skills to be able to run these jobs on your own, and then unleash you to experiment with the code and try to learn some chemistry about the systems that are of interest to you. Oh, yeah. Let's see, and that was me hitting the wrong button. Let's see. So I'll just start with sort of a brief high-level overview of the types of solvation models that are available in Q-Chem. This is discussed in a lot of detail in Chapter 10 of the manual. There's an entire section on solvation models. So at the top of my outline, you see the Kirkwood-Onsager model. This is a generalization of the older Born model of solvation. So back in the 30s, Born solves Poisson's equation analytically for a point charge centered in a spherical cavity, and then Onsager comes along after that and solves Poisson's equation exactly for a point dipole centered in a spherical cavity, and then Kirkwood comes along subsequently still and shows that one can compute the exact solution of Poisson's equation, in other words, the reaction field electrostatic solvation energy of an arbitrary multipole centered in a spherical cavity inside of a medium of dielectric constant epsilon. And so in Q-Chem is this so-called generalized Kirkwood-Onsager solvation model where one computes the electron density with a QM SCF level of theory, and then the code will decompose that into a multipole expansion, and since there's an analytic solution for how a multipole interacts with a continuum solvent, one can compute the continuum solvation energy in that way. The problem with these methods is that they always assume that your molecule is strictly spherical. And from my point of view, Kirkwood-Onsager methods have largely been superseded by some of the polarizable continuum models that I'll discuss later, where the cavity that defines the interface between the atomistic solute and the continuum dielectric solvent is allowed to be molecule shaped. You can get some idea of this from the picture that's on my title slide, where we have glycine centered in a cavity that's built from a union of atom-centered van der Waals spheres. And we can use the exact electron density to compute the electrostatic potential arising from the solute electron density, and then use that to induce a polarization from within the continuum dielectric solvent. Okay, so I will have nothing further to say about Kirkwood-Onsager models. I'm also not going to say anything beyond this slide about the Langevin dipoles model. This is a technique that was developed in Ariel Warschel's group about 10 to 15 years ago, and it's based on discretizing the solvent into a lattice of inducible dipoles, and then using the the solvents, the solutes electrostatic potential to induce those dipoles. And I've given you a couple of references there to the work of Warshall and Jan Florian, who wrote the code. That code has been interfaced with Q-Chem. But so the two things that I am going to focus on today are the last two bullet points on this slide. The first of these is the so-called Solvent Model 8, developed jointly in the groups of Chris Kramer and Don Trular in Minnesota. And this is not quite the latest, but is one of the more recent versions in a long line, at least 8, you will see. Solvation models, and these are highly parameterized models that are specifically intended to reproduce free energies of solvation. And I'm going to tell you that if your ultimate goal out of running these the Q-Chem, running Q-Chem with solvation models is to compute delta G, then I think probably SM8 is your best bet. That largely has not been the focus of what we have done in my research group, and so a lot of our interest in continuum solvation models has fallen into this class of so-called apparent surface charge polarizable continuum models, which nowadays that term is used basically synonymously with the term PCM. Okay, so if we move on to the next slide, so you can ask the question, what would we like to do with a continuum solvent model? And the obvious thing that we would like, that one might like to do is to compute a free energy of solvation. And so as I've suggested, the Kramer-Trular SM8 model is probably the best thing that we have to approximate a free energy of solution. Certainly, it will get you there with the least amount of fiddling around on the part of the user, and we'll get into some examples of that in some aspects of the theory in just a moment. So, what might we want to do with a continuum model other than computing delta G? And actually, I told you that my group has not had a lot of interest in trying to compute delta G's. What we are actually interested in are a lot of condensed phase QM and QMMM calculations, and what we have historically used PCMs to do is to provide boundary conditions. And so, in a sense, this is a less strenuous task on your solvation model, that we need the solvation model not to compute an accurate energy difference between the gas phase and the continuum. We simply need the solvent model to hold our atomistic solute region. It's atomistic, but part of it may be described with a force field, so there may be some QM part, also some atomistic MM part, and then surrounded by a continuum dielectric. We simply need the continuum dielectric to hold the atomistic part of the solute in a reasonable geometry. Okay? And that's going to put other demands on our solute model. Namely, we want to do geometry optimizations, and we want to do potentially molecular dynamic simulations, ab initio MD or QMMM dynamics, in relatively complicated systems where a relatively large region is treated atomistically. And so that's going to put very strenuous demands on making sure that our continuum solvation model preserves smoothness of potential energy surfaces. Okay, so with that in mind, I'm going to discuss these two topics in the order that I indicated. I'll first talk about SM8, and then we'll come to talking about PCMs a little later on. So this SM8 model, version 8 of the Kramer-Trular solvation models, as I'm showing you here, is give you a little bit of theoretical background, not too much, but basically it consists of an electrostatic part and a non-electrostatic part. The electrostatic part falls under the rubric of what gets called a generalized Born model. So you can see a formula here for what I've called G electrostatic, and if you're familiar with Born's formula for an ion centered in a spherical cavity, centered in a continuum dielectric, this looks very very similar to that, and basically this generalized Born formalism is a way of decomposing the electrostatic interaction in a pairwise additive way. So I and J are indexing atoms of your QM solute, and then there's some 1 over F effective Coulomb operator that's known in some limits, but in the end will simply be some parametrized analytic function. The Q's that show up in this expression are partial atomic charges that are obtained by decomposing your electron density or wave function for your QM solute. And within SM8, those partial atomic charges are obtained by a Mulliken type procedure. They're not exactly Mulliken charges. They're so-called CM4 charges, Kramer and Trular charge model 4, but it is a Mulliken-like procedure, and because of that, it's susceptible to some of the well-known problems experienced by Mulliken charges when one tries to use extended basis sets. So computing Mulliken charges in extended basis sets is generally not a good idea, and for this reason, the Kramer-Trular SMX models are parameterized only for relatively small basis sets, so things on the order of 631G star, where the Mulliken charges or the CM4 charges tend to be fairly stable. And so Kramer and Trular in some of these papers that I've cited at the bottom of the slide will give some recommendations about basis sets and density functionals that they think are appropriate for use with their solvation model. And then the final aspect of these SMX solvation models, and one that proves to be important for obtaining accurate free energies of solvation, are the so-called non-electrostatic terms in the potential. And for some reason, part of this slide has gotten cut off. But basically, what the part on the right that's not showing up is telling you that CDS here, so you see this is written as G, as in free energy, subscript CDS. So the CDS terms are, CDS stands for cavitation, dispersion, and solvent structural changes. So it's basically everything that is not the electrostatic interaction of the solute in the continuum solvent. So there's a cavitation energy which is associated with the energetic cost of carving out a cavity in this continuum solvent into which the molecule is going to get placed. Dispersion are the van der Waals interactions between the atomistic solute molecule and what would be the atoms, the molecules of the solvent. And then solvent structural changes largely is short-range hydrogen bonding effects and the fact that the presence of the solute modifies the structure of the liquid relative to the neat solvent. And in the SMX models and a wide variety of other continuum solvation models, these things essentially get parameterized in terms of exposed surface areas of the various solute atoms. So those are the quantities AI, and then there are some surface tension parameters that Kramer and Trular have fit. So it's perhaps more than you ever wanted to know about what goes into these models, but at the end of the day, what you want to do with these models is to compute delta G of solvation, and so let's just look at some error statistics that I took from a short review article by Kramer and Trular. And Trular's group has assembled a large database of experimental solvation energies, and so you can see the ends are listed here, so 940 neutral solute molecules and growing. And then you see listed the mean errors in delta G of solvation relative to experiment. And so for neutral solutes, the errors are actually quite good, less than a kcal per mole. And one can argue that the experimental errors are probably not significantly smaller than fractions of a kcal per mole. You will also notice that that the performance for ions is considerably worse, and that is a general feature of continuum solvation models more generally. For one thing, especially in aqueous solution, the solvation energies of charged species are simply much larger than the solvation energies of neutral species, and so a constant fractional error is going to show up as a bigger absolute error if your species is charged. And in particular for anions, where the errors, again, more generally than simply the Kramer-Trular models, the errors for anions tend to be somewhat larger than the errors for cations, and you can see that reflected in these data. And one can argue that probably has a lot to do with the fact that anions have tails of the QM solute wave function that penetrate out further into the solution as opposed to neutral or cationic solvents, and so those are effects that are either absent or are in general simply very difficult to describe with a continuum solvation model. But anyway, these numbers, I think, this paper now is 5 years old, and there is at least one generation of Kramer-Trular model beyond what's available in Q-Chem, but I think that this really, I still think that these data give you some sense of what is the state of the art in terms of the errors that we can expect in delta G's of solvation. Okay, and so I'm going to ultimately now go on to talk a little bit about the theory behind polarizable continuum models, but before I do that, I thought that I would switch to showing some examples of setting up inputs. So I haven't bothered to try to copy these onto slides, but I have set up a directory here of test jobs that I hope that everyone can now see my shell. And I've run a job that I called SM8. So if I go in and take a look at this with my favorite graphical user interface for Q-Chem, which is VI, we have a much fancier graphical user interface now, IQMol, which there was another webinar about by Andrew Gilbert, but I have still not, I've been using VI for so long, I haven't totally converted over, so this is what you're going to get. So this particular test job, even though it says at the top it's MO6 for whatever nefarious reasons, I actually ran it with B3LYP, so let's change that. So this is 5-fluorouracil. As I said, I'm not going to deal too much with the chemistry or the physics, so the identity of the molecule is largely irrelevant. But basically what is relevant is setting up the job, and it's really incredibly easy. I set up my exchange Hartree-Fokker DFT. I choose a basis set, and then I tell it SMS solvation equals true. By default, all of our continuum solvation models are going to default to a dielectric constant for water, so epsilon equals 78 point something. There is a rem variable that you can read about in the Q-Chem documentation, SMX underscore solvent, which takes a string that's equal to any of a long list, and now we're looking at the Q-Chem documentation here, and you can see that there's a quite substantial list of the number of solvents, actually quite substantial, it goes on for 2 pages, of the solvents for which SM8 has been parameterized. Okay, but I just ran this for water. The solvent to have if you're only going to have one, and so what you're going to see, first of all, is when you run an SCF calculation with a continuum solvation model, you're going to get a lot of extra output relative to the nice, clean output that you're used to seeing, and that's because we were sort of sloppy and left some of our debugging statements in. Okay, let's think about what we're seeing here. So as I scroll down through the input section, coordinates and whatever, SM8 is going to run a gas phase. A gas phase calculation first, and that's going to provide a good initial guess for the electron density once we turn on the continuum solvent. And so we're iterating here through the gas phase SCF. That then converges to something. We get a list of the atomic radii that are going to be used to construct my solute cavity. As is usual for this field, it's a slightly different solute cavity is used for the electrostatic and the non-electrostatic part. So G_P is the polarization or the electrostatic parts of the energy, and then CDS, I've already told you, are the non-electrostatic parts. And now we see a listing of the parameters that have gone into this model, and now, starting here on the line that talks about cycle and energy and dice error, we're going to start iterating again. But now, at every iteration, you see that there are some atomic partial charges that get printed out. And those are the atomic partial charges that are then used to compute G_P, the polarization part of the solvation free energy. So this iterates for a while, ultimately converges here after 7 cycles, and then we get a list of various components of the solvation energy, and I'm not going to read through all of these. You can sort of go through these in the privacy of your own homes. But the final solvation energy here, delta G S, so solvation in the liquid free energy of solvation minus 12 kcal per mole. Okay, and now I haven't bothered to do a geometry optimization for my solution phase molecule. That's something that one could easily do simply by choosing job type equals opt. And so if I really wanted an apples to apples comparison relative to the gas phase, I would want to optimize separately my gas phase geometry, obviously using a standard gas phase quantum chemistry calculation, but then also optimize the solution phase geometry simply by doing an optimization with SM8 turned on, and then that energy difference would be reflective of delta G of solvation. Sometimes those geometric corrections to the solvation energy for relaxation of the geometry in solution are small. I won't guarantee that they will be small in all cases. Okay, and then we get molecular orbitals, etc., and various other things, but now molecular orbitals that are polarized by the continuum solvent, and we get somewhere down the line. Molecular orbitals. Anyway, so that's what I wanted to say about SM8. So back to my theoretical slides. So this now is the material that I'm honestly slightly more familiar with. I had absolutely no role in either the construction or the implementation of the SMX models. I did have some role in developing both the theory and the implementation of these so-called polarizable continuum models. However, the people who have had a more important role in developing this theory primarily is the Tomasi group in Italy, and then various of his descendants. So he's trained a long line of PhD students who have gone on to work out the theory, and you can see references to a couple of Tomasi's review articles on this slide. And then a little more recently, Dan Chipman at the Notre Dame Radiation Lab has also made some contributions to the theory, and I've given you a reference to one of his review articles, and I will give you a very brief overview of the theory here. So the basic idea, as with most continuum solvation models, is I'm going to have a solute molecule treated atomistically, and then I'm going to define some sort of a cavity that that defines the interface between the atomistic region and the continuum dielectric solvent. You know, as you can sort of infer from the picture here, that cavity is in this particular example is a union of atom-centered van der Waals spheres, and then these polarizable continuum models are going to use the solute's electrostatic potential, which we know exactly once we do a QM calculation for the electron density. That electrostatic potential is going to polarize the continuum solvent, and the net effect of which is a buildup of charge on the surface of this cavity. And so in my figure, the cavity surface is colored according to that induced surface charge. Okay. And now there are a number of things, of different models that fall under this general formalism of polarizable continuum models, and frankly it's a little bit of an alphabet soup that was fairly intimidating to me when we first started working on continuum solvation models a few years ago. So I will try to, you can benefit from me having scrutinized the literature in this field. Sort of at the top of this hierarchy is what gets called the the integral equation formalism, or the IEF-PCM. And the IEF-PCM is equivalent to an exact solution of Poisson's equation for all of the solutes charge density that lives within the cavity. And so insofar as none of your electron density penetrates outside of the cavity, this really is the exact solution to the continuum electrostatics problem, which is defined by Poisson's equation. In addition to which, it includes an approximate correction for the so-called volume polarization effect. That is the polarization of the continuum based on the tails of the electron density that have penetrated outwards beyond the solute cavity. Okay, and then there are various other forms of PCMs, things that maybe you've heard the acronyms of, like COSMO, that I claim can be viewed as approximations to this sort of overarching theory that we call the IEF-PCM. I'll have a few comments to say about that. So this is sort of reiterating a little bit. So the integral equation formalism is an exact solution to Poisson's equation for all of the charge which is contained within the cavity, plus an approximate correction for the escape charge, or the so-called volume polarization. One can make the argument, because it is starting with an exact solution to a well-defined model, namely Poisson's equation, that this is a more first principles way to do the electrostatic parts of a free energy of solvation as compared to the highly parameterized models of Kramer and Trular. On the other hand, I should warn you that absent some very careful inclusion of non-electrostatic terms, you are probably not likely to approach the accuracy of the SMX models for delta G's with IEF-PCM calculations. And I'll show you some data in another couple of slides to back up that claim. And now, by way of explaining sort of a slightly confusing nomenclature in this field, if you read Dan Chipman's papers, you will see reference to a model that he calls SSVPE with specially placed parentheses around the V. And this stands for the surface and simulation of volume polarization for electrostatics. And it turns out that at the level of formal integral equations, Chipman's SSVPE model is completely equivalent to what we call IEF-PCM, but the mathematics that got you there was quite different, and it wasn't realized until both models were published in the literature that they really were equivalent, and hence they wound up with different acronyms. There is a little bit of ambiguity as far as how one takes those integral equations and discretizes them to get the finite matrix equations that we actually solve in Q-Chem. And if you are interested in this point, which frankly is a little bit esoteric, but if you're interested, we've discussed this at length in the chemical physics letter that I wrote with Adrian Lang that's cited on this slide. I should mention that Dan Chipman's original implementation of the SSVPE model, which is in Q-Chem, uses a quite nice cavity surface construction that does not involve a lot of adjustable parameters. Namely, if we go back to this figure of the cavity surface, he is going to define the cavity as an isodensity contour. So it is the locus of points around the molecule where the electron density is equal to some prescribed value. He tends to use 10 to the minus 3 atomic units as his prescribed value. And so that is a one parameter way to define what we mean by the solute cavity, as opposed to using some sort of atomic van der Waals spheres where you potentially have one parameter for each atom type, namely a van der Waals radius, and then maybe an overall scaling factor. The de facto standard for constructing these cavities is to take radii that are 1.2 times the van der Waals radii. So you wind up with a number of adjustable parameters, and the results that you get tend to be highly sensitive to those parameters. So the good news is that Chipman's model reduces the cavity surface construction to a single parameter. The bad news is that the gradients, the energy gradients for isodensity cavity are quite complicated, and actually, to the best of my knowledge, no one has worked them out and implemented them in any electronic structure code. And so for Chipman's isodensity cavity construction, no analytic gradients are available. Any geometry optimizations that you want to do will have to be done by finite difference. And that is done automatically by the code, but can be quite expensive. Okay. In contrast, my student Adrian Lang and I have implemented a version of the IEF-PCM, or if you like, SSVPE Solvation Model that does use atom-centered van der Waals spheres to construct the cavity. So with the caveat that one needs to be very careful about what radii one chooses, it is at least relatively easy to write down analytic energy gradients, and in fact we have implemented analytic energy gradients for our implementation of the IEF-PCM SSVPE Solvation Model. The last thing that I would like to point out by way of the complicated nomenclature of these models is the so-called Cosmo model developed in the 1990s by Clampton Sherman, or more precisely the generalized Cosmo or G-Cosmo model that was developed by Trong and Stefanovic, which turns out to be formally equivalent to what Barona and Cossi have called the conductor-like PCM, or CPCM. So G-Cosmo is fully equivalent to CPCM, and these things differ by a dielectric dependent factor, so differ only very slightly from the original Cosmo model, and in fact in high dielectric solvents that difference is inconsequential. And in fact, in high dielectric solvents, I claim that these Cosmo-based models are basically very nearly numerically equivalent to this somewhat more complicated and computationally evolved IEF-PCM formalism. And so you can go and see my paper, which is cited there if you'd like an analytic proof, but I can give you a numerical proof right now. If we compare the black curve here, which is for the Cosmo or conductor-like PCM, this is looking at the solvation free energy as a function of dielectric constant of the solvent, and then compared to the red symbols, which is the version of IEF-PCM that we have implemented in Q-Chem, what you can see is that in low dielectric solvents, so when epsilon is on the order of 2 to 4, which is consistent with a nonpolar organic solvent, you can see that there is a couple of kcals per mole difference between the black symbols and the red symbols. And the red symbols, remember, are a model which is exact for all of the charge which is contained within the cavity. And CPCM is an approximation to that exact result. But it's an approximation whose leading error term goes like 1 over dielectric constant. And so in high dielectric solvents, and in particular by the time you've gotten to epsilon equals 80 for water, there is essentially no difference in the free energies predicted by these two models. The conductor like PCM is less computationally expensive, and so this is what we use basically exclusively in high dielectric solvents. Okay, now returning to this data table from Kramer and Trular, but now unveiling some additional columns of data. Kramer and Trular have gone and run a few different continuum solvation models, which includes the IEF-PCM model as implemented in Gaussian 03 with a particular cavity construction that's the UA0 in the third column of numbers. They've also looked at CPCM as implemented in games, and G-Cosmo as implemented in W-Chem. And the take-home message from all of these data is that you see that the error statistics really are simply a lot larger in looking at these other things than they are with SM8. I will point out, and I pointed out in my note in red, that the two models that I've highlighted in red at the level of integral equations are formally equivalent, and so this gives you some. But if you're looking at the columns of numbers, you see that the numbers are quite different, and without having actually run these calculations in games or in W-Chem, I can't tell you what the exact reason is, but presumably these two codes are using a different construction of the solute cavity, and so looking at the differences between the two columns of numbers gives you some indication that the free energy of solvation really is sensitive to how you parameterize the cavity. Well, this Kramer and Trular paper generated a little bit of controversy in the literature, and so just to pay some service to that, I will point out this subsequent Accounts of Chemical Research paper by Klampt and Tomasi and co-workers who wanted to sort of defend PCMs by showing that it is possible within a PCM formalism to get errors that are comparable to the errors in delta G that one gets with SM8. And so in particular, if we look at the data that are called Table 2 and the model that's called IEF-PCM/MST, you see that the errors there look quite good. So sub kcal per mole errors in delta G for non-aqueous solvents and errors of about 1 kcal per mole for aqueous solvation. This MST model is, MST is three people's initials, the T is Tomasi, is an IEF-PCM calculation supplemented with non-electrostatic terms, and really is necessary to, it's crucial to supplement with those non-electrostatic terms in order to get free energies of solvation that are comparable in accuracy to what one can get with SM8. Those non-electrostatic terms for use with the IEF-PCM have been implemented in Q-Chem, but I will be perfectly honest, and is based on these papers by Flores and Tomasi that are cited at the bottom of the slide. But to be perfectly honest, my group has done very little with trying to actually compute delta G's of solvation. And so I would say use at your own risk. And actually, I'm more than happy to see people experiment with this, and I'd be curious to know whether those experiments were successful. But I think this is a case where you will absolutely have to consult the primary literature to see the types of parameters that Flores and Tomasi are recommending for these non-electrostatic terms. But in terms of how to set up your Q-Chem input files to augment IEF-PCM with these non-electrostatic terms, all of that setup is well documented in the Q-Chem documentation. Okay. And so now, going on a bit longer than I had expected, and I do want to have some time to take some questions. So maybe I will sort of blow through some of these last parts sort of quickly. But let me switch back to my shell here, because I did want to give you some idea of how to run these PCMs. So I'm going to open up a job that I've called PCM1. Go up to the top. And allegedly this is trifluoroethane in water solvent. And so we're going to set these up. The setup here is actually quite straightforward. We choose a basis, we choose a density functional or Hartree-Fock theory, and then we choose solvent method equals PCM. And then, if desired, we can choose some additional job control parameters in a $PCM section. Actually, most of these have sensible defaults, but just to illustrate their use, I decided to define them. In some cases, I am using the default values here, but what I'm doing in this $PCM section, I'm setting theory equal to CPCM. So rather than using this exact IEF-PCM, we're going to use the conductor-like model. Because, as you can see down here in this PCM solvent section, I'm using a dielectric constant that's appropriate for water, and there's really no reason not to use CPCM for the electrostatics in water. I'm using a discretization method called SWIG that I'm going to come to in a few minutes. I'm explicitly inverting the matrix equations, and I'll come to that in a few minutes. I'm using Bondi van der Waals radii to construct my solute cavity, and then I'm going to scale those radii by a factor of 1.2. Bondi, by the way, is a gentleman who compiled a tabulation of atomic van der Waals radii by looking at a lot of crystal structure data back in the 60s, and those are the most popular choice for atomic van der Waals radii for use in PCM. So if we just page down through the rest of this job, we see that we get the normal sorts of things that one expects when iterating through self-consistent field cycles, but in between each SCF cycle, we get a bunch of other junk that maybe someday we should go back and clean up. But we iterate and we iterate, and eventually we converge after 8 cycles, and then we get a printout of various things, and so we get a G underscore electrostatic, which is the electrostatic parts of the solvation free energy, and then we get nothing for cavitation, dispersion, or repulsion, because I have not included any non-electrostatic corrections in this particular sample job. And then you can see various other things in this printout. Okay. Let's see. There are a few other sample jobs here, but maybe I'll go back to my theoretical slides, because I do want to spend a few minutes telling you about what my group has actually contributed to this field, and then, however long it takes me to get through these last slides, I will make sure that I spend a little bit of time answering questions at the end if there are questions. Okay, so I told you that there are 2 things that one might want to do with a continuum solvent model. One is, of course, to reproduce a free energy to compute a free energy of solvation, but the other thing is simply to use the continuum solvent models as boundary conditions. So my group over the last few years has done a lot of calculations on DNA. So there's a chunk of double-stranded DNA shown here. This would be a large calculation by QM standards, obviously, and in fact, we have not done any QM examples that are this big, and so what we're actually doing is a QM-MM calculation where the MM part is this decamer, I believe, of DNA. DNA is a highly charged polymer, and so if I simply take that QM-MM calculation with a couple of nucleobases treated as the QM region, the rest of this decamer of DNA treated as the MM region, if I take that QM-MM region and put it in the gas phase, I will get nonsensical results because of the enormous repulsion energy between the negatively charged phosphate groups. And so in this particular example, I absolutely need some sort of a high dielectric solvent simply to screen the charges between the negatively charged phosphate groups on the background, on the backbone. And so actually, this is how my group got into wanting to code up continuum solvation models to put in Q-Chem. And so the idea here is that we're going to have, again, a molecule-shaped cavity that defines the interface between the atomistic region and the continuum solvent. But then we're going to have to discretize that because we're going to want to compute an induced surface charge on the surface of that cavity, and that induced surface charge is going to be discretized into a set of point charges. So those are the purple dots that I've shown you here. And you can sort of see that the cavity looks like a union of atom-centered van der Waals spheres. The difficulty is that for this very complicated large molecule, when I start to optimize the geometry and let the atoms move around, or heaven forbid if I wanted to do dynamics, the number of discretization points is going to change discontinuously as a function of the geometry of my atomistic region. And that is a serious problem in that it introduces discontinuities into my potential energy surface. Okay. There's a second issue here that I've indicated in red at the bottom. So there's you know, by implementing this continuum solvation model, we solve the problem of the phosphate groups running in fear of one another because now there's a high dielectric solvent to screen them out from one another. But we introduce two new problems, namely discontinuities in the potential energy surface. That will have some problems, the manifestation of which I'll describe on the next slide. And then secondly, for this large molecule, the number of discretization points of the surface is quite large. And computationally, solving for those induced surface charges is equivalent to solving a set of linear equations, the dimension of which is equal to the number of purple dots. And in other words, the size of your cavity surface scales with the size of the MM region, not the QM region. And the MM region might be quite large, which means that the cost of the PCM actually could come to dominate the cost of the total calculation. So that's something that we're going to have to deal with. Okay, so let's deal with the first problem first, namely the discontinuities. And so what I and my student Adrian Lang have done is to take an earlier idea from York and Karplus, so all of the relevant literature is cited here, and to generalize it for the entire class of apparent surface charge polarizable continuum models. And we get a discretization approach that we call the switching Gaussian, or the SWIG discretization, for reasons that will become apparent. So suppose I have two, for simplicity, I'm just going to take two atoms, A and B. There's a van der Waals sphere or van der Waals circle around each one. And the idea is that I'm going to want to discretize my surface charge into a set of point charges that live on the surface of the cavity, Q1, Q2, Q3, etc. And so the first thing that we're going to do is to introduce a switching function that is going to attenuate those surface charges in a continuous and smooth fashion as they pass into the interior of the cavity. And so at the top of this diatomic molecule, you see, you know, there's a cusp where the two spheres come together, and when one of those point charges moves inside as a function of geometry, rather than just turning it off in a discontinuous fashion, we are going to smoothly attenuate it, its contribution. So that fixes the problem with with the discontinuities. It's that simple. The difficulty is that actually introduces some Coulomb singularities because it allows point charges to get closer together than they ordinarily would have, and so on top of that, we have to add a Gaussian blurring of the point charges, which I've tried to indicate with these gray circles. Then there's some other technical things dealing with this diagonal elements of this D matrix that I don't think I want to go into. So the two key elements are a switching function to remove the discontinuities and a Gaussian blurring or a Gaussian regularization of the Coulomb interactions to get rid of any singularities. Okay. And just as an example, the first example that we looked at to show that this was important is a arguably slightly unrealistic example. We wanted something that was big and floppy, and so we took an adenine molecule in 2 solvation shells of explicit water molecules, and so all of the atomistic region is shown, and then there's continuum solvent everywhere else. And if we go and try to do a geometry optimization of this molecule, using some older discretization approaches, citations for which are given here, but which are known to have singularities and discontinuities, you'll notice that there are these sharp discontinuous spikes in the energy as a function of optimization step. Okay. So that's bad. It stands to reason that those kind of features are probably going to hamper the convergence of your discretization of your geometry optimization. And so if we use the switching Gaussian approach, instead we get an energy that converges smoothly and monotonically to 0. And so we're quite pleased with that. The other nice thing that comes out of this is what one finds in some of these discontinuous approaches is that if one actually plots the surface charge distribution, occasionally there are holes in the surface charge distribution, whereas with the SWIG surface charge distribution, which is shown on the left, you see that it's nicely continuous across this whole cluster. Okay. Another potential artifact of having discontinuities on your potential energy surface, if one wants to do vibrational frequency calculations with a continuum solvent, right now only analytic first derivatives are available. There's a group in China actually that is working on analytic second derivatives, and so those will be available in some future version of Q-Chem, but for the time being, only analytic first derivatives are available, which means if you try to do a frequency calculation, the code will default to finite differencing the first derivatives in order to get the second derivatives that are needed for the frequency calculation. And it's quite possible that those finite difference steps can land on singularities. And so what you see, if you compare the vibrational spectrum computed with our discretization scheme, which is the red data, to one of these discontinuous discretization schemes, which is the blue data, there are extra peaks in the blue spectrum, and peaks at unreasonably high vibrational wave numbers, 10, 11,000 wave numbers. And so clearly nothing is vibrating at 10 or 11,000 wave numbers, and so those are artifacts of discontinuities or possibly singularities on the potential energy surface which are not present in our smooth discretization scheme. Okay, and then the final consequence of having a continuous potential energy surface is that molecular dynamics is stable. Any of you that have familiarity with molecular dynamics know that you must have a continuous potential energy surface in order for your simulation to conserve energy. So as a fairly rigorous test of whether our potential energy surfaces were smooth enough for molecular dynamics, we looked at the reaction which is shown at the top of the slide, which is simply the tautomerization of glycine in water, in a continuum representation of water. So actually in the gas phase, the most stable tautomer of glycine is the structure that's shown on the left. But in a high dielectric solvent, you will stabilize the Zwitter ionic form. And so what we've actually done in this particular calculation is to take the neutral tautomer on the left, flip a switch that says now you're in water, and so we see a spontaneous intramolecular proton transfer. And we chose this as a rigorous test of energy conservation because you can imagine that in this proton transfer reaction we are dramatically changing the shape of the solute cavity as a function of time step as we move this proton from one atom to the other. But then if you look at the energy fluctuations in the graph, and I've blown them up, in black are the energy fluctuations that one gets in a gas phase MD calculation, and there the fluctuations are simply a consequence of the finite time step, whereas the fluctuations in red are with our smooth implementation of continuum solvent, and you see that the fluctuations are no bigger than they are in the gas phase. And so again, the fluctuations are caused by integrating Newton's equations with a finite time step, whereas if we have a discontinuous potential surface, you get the energy fluctuations that are shown in blue, and the simulation simply fails to conserve energy. And in fact, after about 75 femtoseconds, lands on some discontinuity that prevents the SCF from converging at all, and the simulation dies. Okay, and these are just some more data. I should go through this quickly, showing you that if I look at the energy as a function of MD step, I can see this tautomerization reaction happen. The red energy data correspond to 1 tautomer, and then after about 2,500 femtoseconds, the proton spontaneously transfers, and I get the blue data. But if I blow those data up, I see that even in the course of this intramolecular proton transfer, where we get a very rapid change in the energy, that change in the energy really is a smooth function of molecular dynamics step. Okay, and then the last topic that I want to talk about, and I really will take questions. I apologize for abusing my time limit a little bit, but as I said, I have no experience with giving these lectures into my laptop, so apparently I'm more verbose than usual. So I said that if we want to use PCM boundary conditions for complex systems, there are 2 problems. The first of which is the discontinuity problem, which it appears that we have solved. The second of which is that the cost of solving PCM linear equations scales like n cubed, where n is the total number of discretization points, and that's growing with the number of mm atoms for a QM mm PCM calculation. So I've shown you the linear equations in the box. Given the solute's electrostatic potential V evaluated at the discretization points, I have to solve some linear equations for a vector of surface charges at those discretization points. And for a sequence of single-stranded polyadenines, which are the data here, you can see that doing a simple matrix diagonalization, which is the straightforward way to solve linear equations, I get a cost that scales cubically with the number of solute atoms. And so by the time I've gotten to a decamer of mm nucleobases, it's taking me about 600 seconds to solve the PCM equation, so that's 10 minutes. And if your QM region is small, you may be spending significantly less than 10 minutes on the Fock build. And so in other words, we've reached an interesting regime where the classical continuum solvent part of the calculation has become the bottleneck. Okay. And so what I've shown, and you can partially overcome that by parallelization, so the green data are parallelized over 4 processors, but it's still n cubed, just farmed out over more cores. So the better way to solve this is to implement a conjugate gradient solver for the PCM linear equations, and we've done that. And so you can see the blue data, even running on a single processor, the cost is growing very slowly as a function of system size. And we've now blown that up to even much larger things, so that we can do quite sizable MM regions efficiently with PCM boundary conditions. And then we can put all of that together and run a molecular dynamics simulation with a QM MM PCM model. And so here's some large system. It's a chunk of DNA bound to a protein, and you can see energy fluctuations over a bunch of time steps. And so you can see that even for large systems, we're getting good energy conservation with these PCM approaches. And so we really think that these are good approaches for large systems. To show you an example of what this looks like, there's a sample job here called Q-Mmm-PCM crambin. Crambin is some protein, the details of which I know nothing about. But if I open this up, there's some QMMM setup stuff here, which I will leave you to read the Q-Chem documentation about how to set up QMMM jobs, and I will simply focus on the PCM part. So what you see is that I am, again, if we look at the $PCM section, you'll see that I'm again choosing the conductor-like PCM. Now we know what method equals SWIG means. That is the smooth switching Gaussian discretization that Adrian Lang and I developed. But now, rather than choosing solver equals inversion, as I did in the previous job, now I'm choosing solver equals CG for conjugate gradient. There's a threshold for converging the conjugate gradient, which has a sensible default, so it's not 100% necessary to specify this. So let's skip down over some of these other things and focus at the bottom on these three keywords: no matrix, precondition, and use multipole. The no matrix specifies that the conjugate gradient solver should not explicitly build any n by n matrices in memory, because there's the CPU cost of these PCM jobs scales like n cubed, the memory cost scales like n squared, and if n is tens of thousands of discretization points for a large QMMM job, that n squared memory bottleneck is potentially significant. And so we can, this conjugate gradient solver that does not build the n by n matrices is linear scaling both in CPU cost and in memory. And then it has an efficient preconditioner that you should probably always turn on if you're going to use conjugate gradient solver. And we can make use of some fast multipole ideas to speed things up. I'll just page down through all of this protein data and show you what this job looks like. The first thing that the PCM code is going to do is to set up the solute cavity, and so you see a list of grid points here. That's probably quite long, so let's skip over it. And then eventually we're going to start on the SCF iterations, and so here you see the first self-consistent field iteration. And there's going to be a bunch of PCM stuff in between the self-consistent field iteration. But now what you see is that in between each self-consistent field iteration, we are iterating on this conjugate gradient solver. And so the 22 steps that you see listed here are 22 steps to converge a single conjugate gradient iteration, or excuse me, a single PCM iteration, and to compute those induced surface charges. And then at the end, the calculation eventually converges. I should note that I've set some printing thresholds high enough that at the end of this calculation, we actually do get a file in this so-called .pqr format, which is a standard format used by protein people that can be read in by various codes like VMD that are used for protein visualization, and we've simply borrowed their standards. This is actually a file that will print out the cavity surface. So some of those pictures that I showed you where I printed out various PCM cavity surfaces were generated by setting the rem variable PCM_print equal to some sufficiently high value, getting back this file, and then reading it into VMD. So then at the end, you see the same sort of energy summary that that you saw in various other calculations that I've shown you. Okay. The very last thing that I wanted to go over, and then I will, but before I take questions, is to talk about, to show you one slide worth of data about discretization of the solute cavity. So we do this using so-called atom-centered Lebedev grids, same kind of grids that are used for the numerical quadrature parts of DFT. And the reason I want to bring this up is you have a choice of how many grid points per atom will be used to discretize your solute cavity, and the default choice in Q-Chem is extremely conservative, which is good from the standpoint of accuracy, but for large jobs may be slightly detrimental from the standpoint of cost. And so you may have reason to want to reduce the number of points, and maybe in some future version we should think about changing this. But honestly, the default was set before we had some of these data, and turns out to be overly conservative. So the data that you're looking at here, if we just read from the vertical scale on the left, which says delta rotation, these are rotational invariance errors as a function of the number of discretization grid points. And so if we look at the black and the at the red and the blue data, so basically we've taken a set of molecules and we've randomly rotated them and then asked how much does the error change, because these grids do make it so that how much does the energy change, because the energy is no longer strictly rotationally invariant anytime that you introduce a discretization grid. And what we've chosen as the default is, I believe, 590 grid points per atom. So if we look at n equals 590, you see that the rotational invariance errors are less than 10 to the minus 2 kcal per mole, which for all practical purposes is 0. That's why we chose that number to be that large. The second graph that's shown on this slide, again, if we just, in the interest of time, look at the scale that's on the left. In this paper, we were calling the solvation energy W. So W is the electrostatic molecule continuum interaction energy, and we're looking at the difference between W with n grid points per atom and W with 1,202 grid points per atom, which we think is basically converged. And so you see that difference goes to 0, of course, as n approaches 1,202. And again, for n equals 590, which is our default, those energetic differences are smaller than 10 to the minus 2 kcal per mole, which is basically 0. But if we go and look at a real calculation, if I go and look at this calculation, which I've shown you before, where I did not set the number of grid points, and I get a final solvation energy of 5.67 kcal per mole. And then I look at a second sample job, which is exactly the same, except that in this $PCM section, I've set 2 additional variables. Heavy points, meaning the number of points to discretize a heavy atom, and then H points, number of points to discretize a hydrogen atom, and I've reduced those from 590 to 194, so significantly fewer grid points. This is a small molecule, but in a larger molecule, this would probably reduce the computation time considerably. And the total solvation energy is 5.61 kcal per mole. And just to remind you, in the previous calculation, it was 5.67. And so this is a case where the defaults probably are overly conservative. And then the very last calculation that I had set up to show to you was to take the same calculation, trifluoroethane in water, but now instead of computing this at the level of CPCM, in my third sample job, PCM3, I have done this calculation using the SSVPE solvation model, which I am claiming is nearly identical to CPCM in water. And in fact, you see that the total solvation energy here is 5.57 kcal per mole. So to two significant digits, the SSVPE and the CPCM calculation are giving me exactly the same solvation energy. So the differences are on the order of 10 to the minus 2 kcal per mole, which is far less than the intrinsic accuracy of any of these solvation methods. Okay, so with that, I've talked half an hour longer than I intended to. So the very last thing that I will do before the moderator comes back and reads me some questions is simply to show you the acknowledgement slide. The 4 papers that are listed here are the most important 4 papers that my group has written about PCMs. They're probably not the most 4 important papers in the entire history of PCM, but I'm giving the talk, so I have some leeway. And then the 3 people and organizations that I should thank are, first of all, Adrian Lang, who was my former PhD student, who was the one that did almost all of this work. And he was supported by my NSF grant. And then we get a lot of computing time from the Ohio Supercomputer Center, so I should thank them as well. Now, Mark has returned and is going to read me some questions, I gather.
Okay, so our first question is, on the DNA calculation, what is the effect of adding counter ions such as sodium?
It's a question that I get a lot, actually, when I give my DNA talk, and the answer is I don't know. The detailed role of counter ions in Q-Chem simulations of DNA is something that is still a little bit controversial. There's a lot of thermodynamic data. I mean, there's plenty of thermodynamic data that show that DNA is very sensitive to the ionic strength of the solution. Right? We can denature the DNA by adding or removing the appropriate counter ions. However, in a lot of Q-Chem calculations, those Q-Chem calculations seem to be somewhat insensitive to the presence of counter ions. Now, I won't claim that that's a universal fact, but certainly in various things that we've looked at, the Q-Chem electronic structure of the nucleobases does not seem to be very sensitive. And now that may well be an artifact of not having sampled the dynamics out long enough to see strange things happen to the DNA. But the honest answer is that I don't know. In the context of continuum solvation models, since that's the theme of the day, I should tell you that you know, it's not immediately obvious how to represent counter ions within a continuum approximation to the solvent. In other words, what is the PCM equivalent of solving, say, the Poisson-Boltzmann equation, or doing a Debye-Huckel type calculation where I have a continuum solvent with a finite ionic strength, and actually that is the second part of Adrian Lang's work on PCMs. They're not papers that are listed here, but they are listed on my website. I didn't talk about those things because I'm not sure that all of them have been officially released as part of Q-Chem, but we actually have managed to generalize Debye-Huckel theory to arbitrary cavity shapes, and so we have continuum solvent models that do include corrections for finite ionic strength. If you know anything about Debye-Huckel theory, you know that Debye-Huckel theory uses a modified Coulomb operator. You have a gas phase Coulomb operator that looks like 1 over R. In a continuum solvent, it looks like 1 over epsilon R. And in Debye-Huckel theory, it looks like e to the minus kappa R over epsilon R. So it's a Yukawa type potential where kappa is the so-called inverse Debye length. And anyway, we figured out how to fold this into continuum solvent methodology, and those models will be released in some future version of Q-Chem. So I'm not sure that was the most satisfying answer, but that's the honest truth.
All right, the next question is, what type of radii and what van der Waals scale should I use for small molecules like guanine, magnesium 2+?
The radii issue is a big one. You can easily verify for yourself. You don't need to take my word for it. You can run the calculations to verify that the solvation energies that you compute, and probably various other properties as well, like vibrational frequency shifts relative to the gas phase that are induced by the continuum solvent. So the energy and various other properties are exquisitely sensitive to how the cavity is constructed. From my point of view as an ab initio quantum chemist, this is maybe the least satisfying part of the whole model, and it's a how to go beyond this is an active research topic in my group and in other groups. So I will tell you that the standard choice that is used probably in the vast majority of PCM calculations in the literature is to use the so-called Bondi van der Waals radii. So radii equals Bondi in your $PCM section, and to scale them by a factor of 1.2. And that factor of 1.2 is a kludge that is intended to slightly enhance the size of to slightly exaggerate the size of the cavity in order to account for so-called solvent excluded regions, where your solvent molecules, if they were atomistic, have finite size, and so should not be able to penetrate all the way to the van der Waals radii of the solute. And so in order to fold that effect in, one scales the van der Waals radii, and 1.2 is the factor that's usually chosen. That being said, my feeling is that this is something that really ought to be tested in a system-specific way. That if if what you are looking for is to reproduce some trends, then it may be that trends are less sensitive to the choice of the cavity construction than the absolute energetics. But if you really are interested in the absolute energetics, I think it's probably mandatory that you have some sort of a benchmark that will tie you to some measurable experimental number that will allow you to gauge what you think of the cavity construction.
This concludes our webinar. We would like to thank John Herbert for his excellent presentation. If you've not tried Q-Chem lately, we have come a long way, and we invite you to utilize our 2-month full-featured demo, which you can request by hitting the orange free demo button on our website. Should you have any questions, please feel free to contact us by emailing either Jinting or Yihan at the email addresses noted on your screen. You might also be interested in viewing some of our other webinars located on the Q-Chem YouTube channel. You can find the link to this page at www.q-chem.com. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.